Okay, good morning. Let's get started. So how is the homework project coming along? I think some of you commented that the code looks pretty ugly, right? The code is very, not exactly the right piece of code to make it easy to parallelize, which is sort of by intent. I don't want it to be trivially optimizable because I think last year someone solved it by mathematically to make it parallelizable. The idea here is not to test whether you can transform the program into a mathematically equivalent problem which is easy to solve, right? The idea here is to see how you can parallelize it, right? It's okay to transform it into some fashion, but don't transform it into a fashion where you don't need locks at all, right? Then that kind of violates the intent of what you're trying to do, because I want you to see how either hard or easy it is to write these programs, right? Make sense? Right? So do you have any questions from what we covered so far in synchronization? We have one more topic we need to go through and to cover chapter 6. It's a fairly long chapter. And it's also, I think, one of the important chapters, because that's the, like I mentioned before, some people consider that if you don't understand this, they believe that you don't really understand computer science kind of stuff, right? So before we go into the atomic transactions, I'm going to go through a little bit about how the different operating systems deal with semaphores and things of that nature. And one of the things to remember from the discussion here was spin locks are good because spin locks you don't have to give up your CPU, so you can kind of get back into the groove. But spin locks are also wasteful. So if you use spin locks in a uniprocessor machine, you're going to use your time slice for doing nothing because there's no possible way somebody else could be releasing the lock. So essentially, you waste your CPU cycles doing nothing, right? But blocking means that you have to give up your CPU, you have to go back on the queue, wait for your turn to come in. So you have to strike a balance. So different operating systems. This is one of the cases where they can make a difference, right? So they can, if you call a semaphore primitives, they can choose the right set of stuff to make your programs go faster. Solaris does that, what they call adaptive mutexes, right? If it's on a single processor machine, they always do a blocking call. But if it's on a multiprocessor machine, depending on how they predict what you're going to do, they can either spin or they can block, right? So it's called adaptive, and it's hoped that depending on what your particular program is doing, you may get better performance either by using the right set of locks. And again, you can come up with the policies of whether you choose spin, you choose the spin, when you choose the blocking. You can argue how significant this will be in a real program, because if you don't use too many synchronization primitives, you may not notice this. But I think your homework project, you'll use enough that you may actually make a difference, right? And they also have a notion of what they call turnstiles. So the idea here is one of the problems with the critical section is you don't have to know who's supposed to run. So there's no ordering, right? So if you have 3 threads come to the critical section, all we guarantee is all 3 of them will get service in a bounded amount of time. You don't say when, right? One way to make sure that they get service in the order that they came would be to have some sort of a queue data structure. So as the threads come along, they kind of wait on the particular queue. So you can kind of go through the queue and then figure out exactly who should work, right? So that's the notion of a turnstile. So if you come to a semaphore and it's locked, then you put yourself on the back of the turnstile, so you can do a first come first serve, right? That's the idea of the turnstile. The challenge here would be that you probably have more semaphores than there are threads in a program, so you don't want to have one turnstile per object being one of the semaphore objects. So the way they implement that is you have one turnstile per thread, right? So when a thread comes to a semaphore, and if it's going to be locked, if there's nobody else there, then your turnstile, the thread's turnstile, becomes the turnstile for the particular lock. When it's done, then the next one who's going to be waiting would be the lead of that turnstile, right? So that's optimization to make sure that you don't have too many queues. Because again, one of the things you don't want operating systems to have lots of data structures because they are memory overhead. So you associate that with the thread who's calling. So if a thread is going to wait on a semaphore, it gives its turnstile as the wait queue for that particular semaphore. And every thread which comes after that would use that turnstile to queue themselves up. And when you get service, you pass the turnstile on to the next one. Does that make sense? Okay. It's a slight optimization because you realize that there is no point in having one turnstile per semaphore. But you potentially could need one turnstile per thread. So that's what you implement this, right? So again, these optimizations really designed for lots of processors where there's contention stuff, right? So if you're running your process as a single-threaded process on Solaris, you wouldn't notice many of the stuff, right? You won't notice any of this stuff because you don't use semaphores or you don't use any of the stuff, right? So why do you think that Solaris was spending all this time on these optimizations? Where would this pay off? Yeah.
Servers or something like that?
Lots of processor server, right? Yeah, server, but you're talking about big servers. You're talking about 64,028 processor or what have you, right? You're talking about a server where there are a lot of processors and there are a lot of threads, and they're all sharing some stuff, right? So they're probably targeting their workloads of large databases, large web server or something where they notice that this is a problem, right? If you have, like, say, 2 processor, it's hard to imagine why you would want to go through all the stuff for 2 processors or so, right? So that's one of the reasons why you may not notice it on a Windows XP, but you may see it on the Windows Server or Solaris or whatever, right? So in the market segment, Solaris at least tried to be on the upper end of the server spectrum. They wanted to be on the super powerful with lots of processors and stuff like that, and this is one of the ways that they achieve that, right? And again, if you look at Windows XP, that's a desktop operating system. So for the most part, when Windows XP was developed, people didn't have a multiprocessor on their desktop, right? So they could solve this problem by disabling interrupts, right? Having some simple stuff because nobody was using threads, so why bother, right? There are a few people who are using multiprocessors, and for them you can have spin locks. You can do the traditional stuff because this was not a problem back then, right? And as we move along, these things may change, right? So I don't think I mentioned it in this class. Can you think of another machine that some of you may use which has lots of processors? How many of you use a machine with 2 processors in your laptop or desktop or whatever? A few of you, right? How many of you use a machine with, say, like 8 or 9 processors? Some of you may use such a machine, right? How many of you use PS3, the Sony PS3? Oh, very few, right? Fewer than the desktops. So if you use a PS3, essentially PS3 it has a 7-core processing engine and a one processor to send the process, right? PS3, the architecture is kind of weird. It's not like a regular processor. Even though there are all these cores, there are restrictions on what they can do. There's restrictions on what kind of interrupts they can create. Sorry. That's my wife, so I can know who is. So essentially, you have restrictions on what the threads can do. So when you program for a PS3, you don't write it's not like a simple threaded application because you can't have interrupts. So these processors are really fast to do some task, but it's not general purpose kind of threads, right? But regardless, those are 7 or 8 processors. I think the hardware has 8 cores, but they only give you 7 core because one is allocated for problems in manufacturing, right? So you have all these cores. So essentially, when you're writing for PS3, that's what they have to do. They have to write this multi-threaded application, right? They have to write. So if you really want to use the full power of PS3, you would have to have 8 different threads at the same time, each cranking away, right? And I think turns out the PS3 hardware is so fast that you could just currently you can have 1 core playing your game, and you won't notice a difference, right? So we were talking to some of the guys who were working on PS3 before PS3 came out, and they were trying to come up with applications which can really use all the 7 cores of the machine to give you a good program, right? So they were trying to do high definition video chat, I think like 2 or 3 video chat with 2 or 3 different people. They could do that with one core, right? They could come up with one example where they needed all the 7 cores to do something massive, right? The hardware can actually drive to, I think, to 1920 by 1080p video, right? 1920 by 1080 means on the video screen you have 1920 pixels here, 1080 pixels here, 30 of them per second, right? That's a lot of data that they're processing, right? You can do all of that with 3 or 4 video chat with a single core, right? So the core is really fast that most of the games you see right now don't really need that much of a power, right? But hopefully sometimes you will need, and when you need, it's not going to be trivial because now you have to worry about threading, you have to worry about all the primitives, right? So the library from Sony would have to deal with whether you do spin lock or what have you, right? So I'm kind of surprised that only a few of you have a PS3, right? Can you think of an application on PS3, or do you know of an application on PS3 which could potentially use all the processors? At least for the people who have PS3s, right? Yes?
So folding at home?
Yeah, I think the folding at home, right? It's a trivially parallelizable application, right? Because basically it runs, it takes a set of data, operates on it in each core, so it can do, because there's no synchronization between those. And I think for folding at home, PS3s are fantastic. I mean, in fact, they shot up to the #1, right? That's because folding at home is essentially it's trivially parallelizable, meaning there's no synchronization among the threads. If you have 10 cores, it essentially takes 10 jobs, and each core works on one of them. When it's finished, it takes the next job, and it proceeds. So there's no problem, right? So unless you are going to write a program which is that trivial, you're stuck with dealing with synchronization primitives, right? And that's one of the problems that Sony will have to deal with. Is how do you train these game programmers to think in threads, not just one thread, but 8 threads running parallelly and doing stuff, right? So Windows XP and to a large extent, Linux also follows a model, because so far we haven't seen many processors, really large processor systems running Linux. I mean, there are very few. So they can still afford to turn off the interrupts if you're on a uniprocessor. And multiprocessor, you would do the traditional stuff we talked about, right? But as Linux scales up to a larger and larger machines, you have to do something like what Solaris and all does, because if you have larger processors, it matters how much performance you can get out of these systems, right? So if you have to, it's good to have critical section where everybody has to wait, but any of the little stuff like spin locks and all those things, you would want to get rid of, right? And the last one is the pthreads, which really has to be the lowest common denominator, because it's a OS independent threading library. So it supports semaphores and mutexes, what have you, and it's not really meant for high performance. It's rather built for portability, right? So these are some examples of how you would build these things, and the takeaway message is, depending on what you're targeting, you spend more energy or not. If you're targeting large number of processors, you spend more energy on that, right? So I'm going to move to the next section, which may be trivial to people who took databases. In fact, it ought to be trivial, because this is essentially moving databases into the operating system, right? Databases, for their living, worry about this. This is all they worry about. You don't really care about the GUI and all those things which are trivial. Fundamentally, they define a notion called transactions, right? That's the reason why you use a database rather than building your own little data structures. You want a notion of a transactions, where the transaction is, you want a set of operations to happen all or nothing, right? That's the notion of a transaction. That is at the core of a database, right? So database, if you took a database course, probably in your first sentence you hear is a notion of a transaction. Right? With the transaction, databases are no big deal, right? So for example, if you want to, let's say, take money from your checking account and put it in your savings account, right? So that may consist of operations like take money from your checking account and then copy it to the savings account, and then write it back into the savings account number. So you have, let's say, two variables. You want to take the variable from your checking account and do some manipulations on it, decrement the value, and then you store it back into the savings account value, right? This is all defined as one transaction because you want them all to happen or none to happen, right? So one of you may like one of the others to happen, but both of you want both of the stuff to happen. What I mean is, suppose you only could do half of the stuff, right? For example, if the bank wrote this transaction as it first wrote the saving and then it wrote the checking, and then something failed, right? So for example, it's taking $100 from your checking, and then it's going to put it to the savings account, right? So if it wrote it as it first updated your savings account, and then it crashed, right? Now what happened was your checking account was the original value, and the savings account was $100 more, right? Which I'm sure none of us would complain bitterly about. If that's what is going to happen, you're going to be happy, right? If it's the other way, where you took the money from the checking account, but then before it could write it to the savings account, it crashed, right? Then the bank won't complain too bitterly because it's okay, because $100 kind of vanished. You would care, right? But what both of you would want is, you want this transaction where something is taken and something is returned back, right? So what you want is either it should happen or not. So either it should be committed, which is called the database terminology to say when it's done. You want all of them to be committed, or you want all of them to be rolled back, right? And that's the stuff that databases community has used. And traditionally, it's assumed that databases are too heavyweight to be put into the operating system, right? That's why you have a database company, you have database products and stuff like that. And traditionally, it's assumed that operating systems have to be simple and all those stuff. But practically, more and more people are bumping into some of these database problems. So you see some of those concepts kind of going into the operating system, because if everybody starts using the same constructs, it might make sense to put in the operating system, right? So for example, inside the operating system, right? You have to move a process from wait queue to ready queue, right? So that means you have to take it out of one queue, and then you have to update the state and then put it on the next queue, right? You run into the same kind of issues there, right? So you're taking, let's say, so suppose you have some data structure, right? A program control block, and this is on the wait queue, right? Meaning this, let's say there's a linked list of stuff, right? And then there is a linked list of stuff for ready queue, right? One way you may do that is you take this data structure off the queue, which means that you need to make this point to here, right? And you take this PCB, you change the state to say ready, and then you have to insert it here, right? If during all this processing, if some things fail, then you have a problem, right? It's more than just locking this stuff. Obviously, you have to lock this data structure so that when you are removing this, somebody does not remove some of the stuff. So you'll have to lock this data structure, but you also have to make sure that when you're doing this and when you're modifying this, when you're putting it back, right? So you want the PCB to either stay here or stay here with the state changed. You don't want the case where the PCB just vanishes, right? Because if it vanishes, then it's not going to happen. So if for some reason while it took it out of this queue, before it put it here, there was some error, right? Which meant that you couldn't put it here because maybe the queue was too big or something. Then you want it to be rolled back to the state where this is in the waiting queue, right? So that's some of the things that you would have to do, right? And traditionally, operating systems didn't want to worry too much about it. How would you solve this? How would you solve this kind of a problem in a simple fashion from what we have learned so far? Let's say within your operating system or within your own applications, right? How would you make sure that not just a simple stuff, but a complicated set of steps are all protected? You can use monitors or semaphores, any of those stuff. But somebody else to try. You get the problem, right? You have you want to take it out of one linked list data structure, and you want to move it into another linked list data structure, right? So you cannot solve this problem by locking this linked list and locking this linked list, because you also have to, after you take it out of this linked list, right? It's now not in any linked list, and you want to make sure that while it's just kind of hanging out here, you don't end up stopping, right? You want something to happen. You want something uncontrollable to only happen when it's here or here, right? What is one way you can solve it using what you know right now? Simple case. I'm not saying how do you solve it the nice way. I mean, some of you may have seen the database way, but how would you solve it right now? Somebody else to try? You can say something. Right? Okay. You will have to sort of make sure that nothing else can do something that's unintended, right? So you will have to, you can't roll back, which is what you'll see in the database language. But you have to make sure that nobody can interrupt, nobody can do anything, right? So it's not okay to just lock this. It's not okay to just lock this. You have to lock this whole thing, right? This whole process of while you're doing this, you cannot let somebody else come in, right? One way to do that is to say, when you start this within the kernel, you disable interrupts. So there's no possible way somebody can do anything, right? So your program is the only one which is running. So essentially, you not only lock these data structures, you lock the whole thing down, right? So if you have some failure, you can undo it, knowing that while the PCB is just hanging around, only you are in control. Nobody else is in control, right? So it's up to your thread. So your thread can do whatever it wants with this data structure. It can do whatever it wants while it's not in any data structure. It can do whatever it wants when it's moved to the data structure. But it's rest assured that nobody else can interrupt into this process, right? Does that make sense? It's maybe not an elegant solution, but that's one way you can do. So if you disable interrupts, that's always the fallback, right? If you disable interrupts, if you say nobody can interrupt me, then essentially you can do whatever you want inside. You have a thread to do whatever inside. And you can do that in your same application program to say, before I want to do this important stuff, I want to make sure that all the threads stop, right? So you can imagine having one lock, and if you have the lock, all the other threads are waiting. They can't do anything else. They can't do anything, even if it's not manipulating this stuff. You want to make sure that while you are hanging in the state, nothing can interrupt the stuff. So you kind of disable the interrupt, right? So that's one way you can solve the problem. That's typically how you do this stuff. And even though that will solve the problem, it's an inelegant solution, right? So if you have more processors, you don't want to stop the whole thing. What you want is, you want such that only the dangerous stuff will be stopped, but the rest of them can let go. And that's why the databases come in, right? Right, so we're going to introduce the notion of some ideas from databases. We can't introduce all the constructs because databases are fairly heavyweight, right? So if you took a database course, you realize that databases are not known to be fast. Their primary goal is to make sure that everything is precise and accurate and do whatever stuff, right? If you want your payroll to happen, you would rather get paid rather than get paid in 10 milliseconds or whatever. Performance is important, but their main goal is to make sure that you get paid and all the data is safe, right? We don't want that bad stuff here, but we're trying to see how we can add the stuff, right? How we can add some of the operations without paying too much of the cost, right? So before we can proceed, some of the definitions that you will have to worry about is the notion of a transaction, right? For a transaction, you need to have a notion of a begin transaction and an end transaction. And just like critical section, it's something that you know in application. You kind of say what they are. And what you really want is whatever operation which happened inside can either happen all at once or none at all. You can never be in a state where only half is known, right? What that means is you may be doing something internally, but nobody else can see the effects of what you're doing, right? Because of course you have to modify variables and stuff, but what you do is, if I'm modifying something within a transaction, and you as another thread wants to read any of the constructs inside, you cannot read anything in the middle. You can only read the status before, or you can only read the status after. If you tried to read something while I'm going through, then we'll do something so that you can never see it, right? In the case of the bank example case, you can never see that the money moved from savings to checking, and halfway through it was nowhere. I mean, it came out of checking, but still not in the savings account, right? Even though in the memory it may be changing, you just want to prevent somebody else from seeing it, right? As long as you keep doing the stuff and nobody sees it, you're fine, because that still maintains the notion of a transaction, right? As long as there's no side effects, you're okay, right? So then once you have the transaction, you have to have a notion of a committed transaction, which means that you're done with the transaction. So it's a begin transaction and an end transaction. When your transaction goes through, then it's considered to be committed, meaning it's all done. There's no rolling back. There's no moving back, which is the next operation we talk about, which is notion of aborted, right? While you're going halfway through, if you find that there's a case where you have to abort, you'll roll back to the original state. In the case of the bank example case, right? So suppose you want to move $100 to your savings account. You took $100. Then you go, let's say, do a check, right, to see if, so maybe your checking account has a limit that you need to maintain, like $2,000 or something, right? So if this $100 would violate that, so it'll try to take the money out, and then it'll notice a violation, in which case it can't proceed forward. So within your application logic, you have to abort. You have to say, you try to do this stuff, and I can't do that, so I have to abort, right? When you do abort, you want to roll back, meaning internally you might have modified these variables, but when I abort it, it'll look as if nothing ever changed, right? So that's important to know. So you may have to modify these things, but all you're trying to make sure is nobody else can see the changes, right? So the way you think of this is like, I kind of lock this variable, I make all the modifications, I keep track of all the modifications I'm making. So if I have to abort, I roll back with all the stuff that I keep track of, and using that, I make sure that nobody else can see what I did. So even though you made some progress halfway through, nobody else can see it, and I can roll back, right? That's the main stuff you have. So once you define a transaction, you as a programmer will have to define a begin transaction, end transaction. And once everything goes through, it becomes committed. If you have to abort for whatever reason, it'll roll back, right? And the data structure that you'll use for keeping track of this is one of the big data structures is a log, right? Before we proceed there, you need to have a notion of three kinds of storage, right? Storage is somewhere where you store the stuff, because what happens is you have a memory variable, you have variables that you're modifying. You have to store these modifications as a log somewhere. So we're basically saying, before I started, your checking account had $900, right? And I did some operation, and then the checking account went to $800, and $100 became savings account or whatever. So you're creating a log of all the things that you're doing, right? And these have to be stored somewhere, right? Not in your program, but somewhere else. And that's why you have a definition of two kinds of storage. One is volatile and one is stable, right? Volatile storage will fail when you reboot the machine. Stable storage is supposed to be stable. So we'll see in the file system what that is. But essentially you want it to be stored somewhere where even if the machine crashes, you still have it, right? And you have a notion of a stable storage, which is more than non-volatile, because you ought to have replication and stuff like that, right? And this is exactly where you spend so much energy in your database world to deal with, especially because if you're dealing with currency and stuff, right? You want to make sure that just because the system crashed in the middle, your savings account is now in a bad state, right? Do you have to worry about that in the same context if you were to move this into an operating system? In a running machine, do you have to make sure that wherever you keep track of what operations are happening, do they have to survive a crash? Do they have to survive a... Because essentially that's what you're trying to do, right? If your machine crashes, you want to make sure that when you come back up, all this data is there. Do you need that all the time, or can you live without it? The notion of stable comes from database, right? But is that important here? Yeah.
I guess not, because like you're only interested in running programs, and if you reboot the OS, back up again.
Yeah. So yeah, you probably don't really need that, right? Because the nice thing about crash is when you come back, everything is lost, right? So you could think about not putting it in stable storage, right? I'm saying it's a nice thing because like a lot of the times you depend on that, right? Because otherwise, when a machine operating system crashes, Windows or Mac or whatever, right, you'll never be able to reboot because you'll keep crashing, right? It's good that everything kind of goes away kind of thing. So as long as you have that, the stable storage may not be as big a deal, right? And that's one place where you get more performance. If you took a database course, this is one of the hardest problems to solve, because what you really want is you want this data to be returned somewhere in a stable storage. And as you will realize that that's very hard to guarantee, right? Which means that I need to make sure that it's actually written on the hard disk, which means that I need to send it from my process through the operating system buffers to the hard disk, and each hard disk has some kind of a cache. I mean, if you look at a new hard disk, it has some memory and stuff. I want to make sure that it actually goes all the way into the disk and is returned on the thing, right? And as you have more and more caches, you can't really be certain that it actually reaches, right? And you don't want to slow down your process to say, I want this one thing to go on the tape, right? So I want the tape arm to move up there, and I want it to write. And most of these big databases are on tapes and stuff. And those are extremely slow, right? So you as a database programmer don't want to say, I'll only proceed at the speed of a typewriter kind of thing, right? I don't want the tape to spin up exactly to write what it has to write, and only after it can be guaranteed that it's written into stable storage can I make the next statement, right? Databases don't do that. They cut little corners and then still try to be good enough, right? But luckily for us, we don't have to worry too much about it, because if the machine crashes, we are fine, right? So the thing, right? So the notion of log-based recovery is fairly easy. So essentially you have a log of all the operations you're doing. So every time you do an operation, you store the original state and then the new state, right? And you store that into a stable log, right? So it's like a little notepad. You keep track of all the stuff you're doing. And this is called the write-ahead logging, because you keep writing ahead of the transaction. So you start a transaction. Every time you modify something, you write it into this log, right? Just because you're modifying and then writing it into a log does not mean it's going to stay. It just means that potentially you could commit, right? Until you had to abort, you had to go back. So in the log, you keep the transaction name, which created it, what's the data name, what's the old value, and what's the new value, right? And so you also start the time that a transaction started, the time that a transaction was committed by the application. So in the log, you keep track of everything. You keep track of when you start something, all the values that you modified, and when you end it, right? If you have to unroll, if you have to roll back, essentially you can either move the state to how it was when your transaction started, or you can kind of roll back from where you are, right? So if it looks like I have to roll back, and I just go back into the transaction log from the latest first, and then see if it turns out that the new value was 100, old value is 50, I just reverse it back. So once I keep rolling back like this, and I come back to the beginning of the transaction, all the changes I made would be erased, right? So you have to make sure that everything is logged. You have to make sure that everything is logged. If everything is logged, then I can roll back. And I can also roll forward, right? So they call idempotent. Once you do this, your whole program becomes idempotent, because I can kind of, from your state, I can move forward, I can move backward, right? To move forward, I have to, wherever you are, right, take the last log entry, whatever was the new value, replace it with whatever was the old value, and I'll keep going back, right? So if I keep going back, eventually I'll come back to this beginning of the program, and if I want to go forward, I take the current value, put the new value, and then I can move forward. Does that make sense? Right. So this log allows us to move forward, move backward. And you need that facility because what you want to do is when you start a transaction, from a transaction you want to keep moving forward till you do abort. When you do abort, you can roll back to where you started. And even though things modified, nobody else would know what happened, right? So these are the properties you need for a transaction. So you need a transaction where you have all or nothing semantics, and you implement that using logs, right? And we'll see that again when you talk about log structured file systems, right? We'll talk about log structured file systems because you have the same problem in a file system where when you're writing halfway through, if things fail, you may be in an inconsistent state, right? So if you remember your Windows 95 or so, when you pull the plug, right, it'll come back and do a scan disk. I don't know how many of you remember those. It'll do a scan disk because it's trying to make sure that all the transactions were fully completed or halfway through. Whereas in the modern systems, you have a log structure stuff, and if you care to look at the messages it prints, it'll say replaying the logs, right? So it'll replay the logs such that you're in a good state, right? You never reach as good as a database kind of stuff because you're kind of cutting corners a little bit here and there, but that's the idea. So we'll see it again in a different context. So like I said, you can keep track of these logs. So the next problem you have to worry about is these logs can potentially become very large, right? So you're keeping track of every operation you do, what the old and new state. That means if your program modifies lots of data, then I'm going to create voluminous amounts of logs, right? So you don't want to create a voluminous amount of logs. So you define a notion of a checkpoint, right? Which is a shortcut which says that I'm not going to keep track of all the state all the way from beginning of time or beginning of the process starting. At some point, I'm going to checkpoint, and all the logs which happened before the checkpoint, I can purge, right? So I save the state of the system at the checkpoint state, and every log before the checkpoint, I don't care. I can only go back till the checkpoint state. I cannot go back any further. So if you want to replay the log, I go back till I hit the checkpoint state. I can move forward. So I can only do this much. So if I choose the checkpoint state to be a good state, but nothing else can change, this will work, right? If I make sure, so for example, in this class, right? If I store the grades up to the beginning of class, I should be okay. I don't need to store the grades before that because that's from a different class or whatever. From an application perspective, I don't really care. I only care about what's the grade for this class. So I can say checkpoint, that will be a good point, right? So you define these different checkpoints, and essentially they're there to make sure that you don't have to keep too many logs, right? Because if you keep the checkpoint to be very far in the back, your log size grows. On the other hand, if it's too small, then you can't really undo a whole bunch of stuff, right? You can't undo past the checkpoint. So you have to do a balance, right? But regardless of what, these whole systems have this overhead of the log. You can make it a little bit less, but that's a benefit. That's a thing you have to pay, right? Databases don't care. Your file systems don't care. So if you do a log structure file system, which is what most of your machines are currently doing, you waste 10 or 20% of the space for logs. But for the most part, it's okay because you don't worry too much about it. But if it becomes large, you tend to worry about it, right? So you write this into the. So that's the notion of a checkpoints, right? Again, this is a notion which is there to for performance reasons, not for any other reason, right? The next notion is notion of serializability, right? So this must have been pounded into you from a database class over, I'm guessing, many lectures, right? I'm only going to go through this in as quick of time as possible, right? So bear with me, it's not a very easy concept to remember, right? The notion of serializability is a notion that if there are two transactions or if there are two threads, I want to let them both run in parallel, right? The solution to all this problem would be to run only one transaction, right? Only one transaction where there's no rollback or roll forward. The solution to all the synchronization problem is to run only one thread. But we don't want to do that because that will not give you performance. What you really want to do is you want to run multiple transactions, multiple threads at the same time. but you still want to get performance, right? So what you want is, as long as you don't interfere with each other, as long as you, so for example, in the bank case, if I'm withdrawing money from my account and you're withdrawing money from your account, we can both be doing the same transaction at the same time, right? Because I'm not looking at your transaction. I'm not reading from your transaction to make anything, right? If it is the case that I moved money from my account to your account, then we are both tied. If it is the case that I looked at your account and then I do something, right? That's a causal ordering, right? So I looked at your account, I see you have something, and based on that, I'm going to make a decision. Those are all part of a transaction. But if you and I had nothing to do with each other, we don't know each other, we don't look at our account, then they can happen in parallel, right? What that means is then I don't have to really care about which order it happened. I only have to care about the serializable order, which states that it may happen any which way, where money can come out of my checking account in absolute time, and split second later or simultaneously it may come out of your account, and so on and so forth. But conceptually, it's the same as whether you proceeded and then I proceeded, or I proceeded and you proceeded, right? Since we don't depend on each other, it's the same, right? What does that make sense? We let both of you, let all these threads, all the transactions run in parallel, but a serializable order means that there exists some possible combination such that if you ran it on a single processor machine, you can say you ran first, then I ran, right? It can be the other way. But it can never be the case where you and I ran at the same exact time, right? In the case where we don't share anything, we don't have to worry. It's trivial, right? If you don't share anything, then we can do it in any order. We can do it in parallel, but you still won't do the stuff. The notion of serializable says that even in the case that we share something, if somehow I can make these stuff such that it appears that there exists a way where one of you, where we both are serial, where one happened and then the next happened, right? If I can transform the operations we did into a fashion where one happened after the other, then we'll see the next slide. It's conflict serializable, which means that even if there's a conflict, it will look like only one happened over the other. So in the case where there's no conflicts, you can run them any which order. In the case where you and I are operating on the same account, if we have this property, that means only one of us can be at the same time. So that means the transaction come into help here, because then it will look like either you went ahead or I went ahead. It will never look like the case where you and I were operating on the same data at the middle, which means that if you're operating on the same data in the middle, the transaction may be violated, right? It may be, you may be seeing some data that I haven't finished yet. So if it looks like you and I were collaborating at the same exact time, and in our transaction, my transaction, I'm looking at my account and I'm moving some money. Your account, you're also looking at my transaction, right? If you're both intertwined like that, then bad things can happen. Because if I abort my transaction, I'm going to modify the same shared variables and transactions will be violated, right? So you need this property to make sure that two concurrent transactions on the same data can proceed. And I'll show the next slide. So when you have conflicts, when you're modifying the same data item, right? If I can guarantee this property, that means two transactions can still appear like it's happening one or the other. It doesn't matter what order, right? Transactions do not guarantee who goes first. They only guarantee that there exists some order where one happens over the other, right? Does that make sense? I want to think about it because for people who took databases, you probably took a lot of classes to get through this. I mean, the notion of a serializable transactions and what have you, right? We don't have much time, so we have to kind of rush through this stuff. But essentially, the idea here is I want to get as much parallelism as possible, but I also want to guarantee that if two people who are operating on the same data were to look like they're conflicting, right? I want the benefit to say that these two transactions will not appear like they were happening parallel to each other, in which case there's a potential that one transaction would have seen the other transaction, right? And as long as I have conflict serializability guaranteed from the operating system, I can define a transaction and a transaction. Operating system can make sure that both of them happen in parallel for performance, but it also guarantees that if there is a conflict, then it'll appear that one went to the other. I will never be able to read halfway through, right? See, if there are two transactions happening one after the other, right? So what it means is the first transaction finishes all its work, and then the second transaction gets that old value, right? Does that make sense? Actually, let me. Let's say there are two transactions, right? And let's say this is I equals 1, j equals 2, and then this I equals j, k equals l, right? If there are two transactions like this, I mean, I don't know what this means, right? But let's say these are two transactions, right? If they are serializable, that means you can either have T1, T2, right? Or T2, T1, right? One can happen after the other one. If this happens, right, I will get a value of j and k will get whatever. And then here, the next transaction will make I equals 1 and j equals 2, right? Or vice versa, right? But if you cannot guarantee serializability, that means there exists no possible serial order one after the other. There exists, it's not this or this, that's a different order, right? Which means that what you might have had is like this. You had, if it happened halfway through like this, right? So this j could have been added here, right? To make it interesting, if you say j equals 3, right? You don't want this I to be 2, right? That means this value of, can you see in the back? Right? So if this happened with after this, right? Then within this transaction, it's getting a value of j which is 2 here. Since it's not committed, it can be rolled back. If it's rolled back, I need to be able to roll this back. Otherwise, I'm going to get part of the transaction which is still going on, right? We don't want that. We want to prevent this stuff. We want either T1, T2. So we want, when it's done, I can either be 3 or let's say j equals 0, right? If you do this expression, I can either be 0, which is what happened before the transaction, or I can be 3, which is what at the end of the transaction was. I can never be 2, right? And that's what you're trying to avoid. So every time you do this assignment, you keep logs, right? And we'll see how we'll solve this in the next lecture. But the notion here is, so if both of them didn't operate on the same data, we don't have to worry about it. We don't have to talk about this, right? See, it is serializable, but we don't really care, right? For example, if this happens to be a equals 2, right? If these two transactions had different variables, then you don't particularly care which order they happen, because even though it's very trivial to make it serializable, but there's no conflict, right? Conflict is when they're operating on the same data, and you want to make sure that you can go with one order, right? And actually, we'll stop with this picture. So essentially, that's what we are talking about, right? So if you have a transaction, one which is doing read A, read B, and read A, read B like this, right? If you want a conflict schedulable, serializable schedule, right? This is conflict serializable schedule. If you think of this as time, even though it looks like some of them are happening in parallel, right? The reason why it's okay is because that is reading something which is not being modified here, right? This transaction is reading A and writing A, which is not being modified here, right? So conceptually, you can move this read and write to like that. Conceptually, this and this are the same, even though this is running faster. If you think of them as time, let's say this took 8 instructions. These two can happen in parallel, so you can actually run it in 6 times, right? So that's what you want to achieve. You get performance, but you get the guarantee that it'll look like this. It'll be a serial schedule, but if you do this, conflict is serializable. Even with the conflicts, it's still serializable to either one. And remember, doesn't matter which order that there is one order, right? It doesn't matter whether one comes after the other, one is the order. We'll continue again with this on the next lecture.